Welcome back. You know, tackling environmental problems often feels like we need these huge, complex fixes. But what if, just maybe, a really persistent issue, like invasive plants clogging up our waterways, had a solution that was almost, well, ridiculously simple?
That's pretty much the idea behind a fascinating 2019 paper we're looking into today. It's titled Full Steam Ahead: Direct Steam Exposure to Inhibit Spread of Invasive Aquatic Macrophytes. The lead author, Kregting, and her team basically sidestepped all the complex stuff.
Right, they skipped the chemicals and the complicated gear and asked, hey, what about just steam? Could a quick blast of steam actually stop these invasive plants?
Exactly. And the target here, aquatic invasive species, AIS, specifically the plants, the macrophytes, they are genuinely disruptive. They create these thick, dense mats underwater.
Oh yeah, they just completely take over. They smother native plants and wildlife. They
Yeah.
make boating or swimming impossible. They mess with water flow.
And that increases flood risks. It's a massive ecological and economic headache. The costs really stack up.
The way they spread is just sneaky. It's not always seeds.
Often it's asexual reproduction. Tiny little pieces breaking off. That's the key.
Okay, let's unpack this. We're talking about these small fragments. The technical term is propagules, right? And they're hitching rides on our stuff.
Exactly. Boats, trailers, fishing gear, waders, kayaks, anything that goes from one body of water to another. We humans are the main transport system.
So biosecurity, stopping that spread before it happens, that's got to be the priority.
It really is. It's far, far more cost-effective than trying to remove them once they're established. Frankly, eradication is often just not possible later on. Prevention is key.
Okay, but we already have biosecurity advice, like check, clean, dry. So if that exists, why the need for something like steam? What's not working?
Well, the issue is often practicality or cost, or sometimes we're not even totally sure how effective the current methods are out there in the real world.
So like the clean part.
Mm.
What's wrong with just washing things down?
We'll take hot water immersion. It sounds good, right? And environmentally friendly. And yeah, studies show water at 45 degrees Celsius or more can kill these plant fragments.
But
But think about it. You pull your boat and trailer out. To do it properly, you'd need to completely submerge every contaminated part in water held perfectly at 45 degrees or hotter for maybe 15 minutes, maybe longer.
yeah, okay, I see. You'd need like a giant heated pool at every boat ramp. That's
Yeah.
not going to happen. It sounds incredibly expensive and just a logistical nightmare.
Precisely. And then you've got chemical options. Disinfectants work, sure, but then you worry about the environmental side effects, the cost again, and are they safe or easy for people to actually use?
Hmm. Plus, you mentioned how small these fragments can be.
Yeah, that's a critical point. Some of these invasive plants can regrow from a fragment with just one node. We're talking maybe 23 millimeters long. That's tiny.
Smaller than a stamp. So just looking over your gear, the check part, that's not going to catch everything. You'd need a microscope.
Pretty much, manual removal is never going to be perfect. So you see the gap. We desperately need something fast, simple, non-toxic, relatively cheap, and something that guarantees these tiny fragments are dead. Right there, right then.
Which brings us back to steam. Using intense heat, but delivered really quickly and locally, instead of that whole prolonged hot water bath idea.
That was the hypothesis Crane and her colleagues tested.
All right, let's get into the experiment itself, because the setup seems really clever in its simplicity. They picked some real villains for this, didn't they?
Oh, yeah. 7 species known for being aggressive invaders that spread easily by fragmentation. Things like Crassula helmsii, that's Australian swampstone crop, and Lagurocephan major, real problem plants.
And what did they actually do to them?
So they took fragments, specifically making sure each piece had an apical tip that's the growing end, the part most likely to root and take off in a new spot.
Yeah.
They put these in little loose clumps of 3.
Okay, got it. Maximize the chance of regrowth potential for the test. Then came the steam.
Yep. They used a standard, off-the-shelf, handheld steam cleaner, nothing fancy. It produced steam at about 100 degrees Celsius.
Boiling point?
Right. And they held it super close, just 2 or 3 centimeters away from the plant clumps, and gave them a direct blast.
For how long? This is the key part, right?
Exactly. They tested incredibly short durations, just 10 seconds, then 30 seconds, a minute, 2 minutes, 5 minutes, really focusing on speed. The control group just got air-dried for 5 minutes, no steam.
10 seconds. That's almost nothing. Okay, but how do you know for sure if a plant fragment is dead after just 10 seconds? It might look wilted, but could it recover?
Excellent question. They needed a robust way to measure mortality. So they developed this neat 11-point scale from 0 to 10 to track degradation.
Okay, break that down.
Basically, scores from 0 to 4 meant it was still viable, maybe even showing new growth. A score of 5 meant it survived but wasn't growing. But scores 6 through 10 showed increasing levels of deterioration. And 10, that was the target. Complete degradation, confirmed mortality, no coming back.
And they didn't just score them immediately.
No, that's crucial. They put the treated fragments into recovery tanks for up to 21 days. They watched them closely to see if anything tried to regenerate. They needed to be absolutely sure that dead meant dead.
What's fascinating here is that quick assessment combined with a longer-term check. You get the immediate visual, but you also confirm there's no zombie-like recovery happening later.
Exactly. They wanted proof of irreversible damage.
Okay, drum roll. What did they find?
Here's where it gets really interesting. The results were, frankly, stunning.
Yeah.
For almost all the species they tested, 6 out of the 7 they achieved that score 10, total degradation, with just 10 seconds of steam exposure.
10 seconds. Seriously?
10 seconds. Confirmed after a standard 7-day observation period in the recovery tanks, those fragments were completely obliterated, biologically speaking.
Wow. 10 seconds to kill off these super invasive fragments that can otherwise survive being broken up and start a whole new infestation. Compare that to the 15 minutes or more needed for hot water. It's not even close.
It's a night and day difference.
Yeah.
And just to be sure, the control fragments, the ones only air dried, they did great.
They survived.
Oh yeah, showed excellent survival, often putting out new shoots and roots. So it proved the steam, not just the handling or drying, was the lethal factor.
Now, you said almost all species. There was one exception.
Right, one slight outlier, Ceratophyllum demersum, which most people know as coontail or hornwort.
What happened with that one?
It still showed significant degradation after 10 seconds of steam, but getting that final confirmation of score 10, total mortality, took a bit longer in the recovery tank, 21 days instead of 7.
Any idea why?
The researchers suggested it's likely down to the plant structure. Coontail has a more rigid, kind of brittle stem compared to the others. It might just take a little longer for the heat damage to fully manifest visually as complete breakdown, even if the lethal blow was delivered in those first 10 seconds.
Okay, that makes sense. It's about how quickly the physical decay happens, but the killing effect is still there and still incredibly fast compared to the alternatives.
Exactly. So even with that slight delay in confirmation for coontail, the overall picture is compelling.
If we connect this to the bigger picture, steam treatments look like a really promising tool. Effective, super fast, no nasty chemicals, and potentially quite cheap. Especially useful where dunking things in hot water just isn't practical.
Let's really hammer that comparison.
Okay, lay it out. Steam versus the old ways.
Right. Remember Crassula helmsii, soaking it in 45-degree water for 15 minutes. Only 90% effective in some studies. That leaves a 10% chance of escape. Steam. 100% mortality in 10 seconds.
It's a huge difference in reliability.
Massive. And then think about just visually checking and hand-picking fragments off your gear. Studies suggest that only removes maybe 88% of the plant material, plus or minus. There's always stuff you miss.
Steam doesn't miss. It cooks whatever it is.
Precisely. It takes the human error, the missed tiny fragment, out of the equation.
So what does this all mean practically? This isn't just lab work. They have ideas for how to actually use this, right?
Absolutely. This study points towards a potential revolution in how we manage biosecurity at access points.
Like putting steam cleaners right at boat ramps.
Exactly. They suggest installing industrial-grade or even just powerful household steam cleaners at places people frequently use: boat launches, fishing spots, marinas, harbors.
I'm picturing something like a car wash for boats.
That's precisely the analogy they use. You could have drive-through stations, maybe operated by staff, maybe self-service, maybe even fully automated arches that steam clean a vehicle and trailer as it passes through.
Wow. Instead of a 15-minute soak, it's a quick zap as you drive out. That changes everything in terms of user convenience.
And industrial steamers can get really hot, like 180 degrees Celsius, and generate high pressure. That means they could potentially blast steam into all the nooks and crannies on complex gear boat hulls, trailers, engine parts, fishing nets, places where fragments hide and are missed by a simple hose down.
Okay, wait though. 180 degrees Celsius? That's really hot. Is there a risk of damaging the boat? The paint? Gel coat? Seals? That seems like a potential hurdle people would worry about.
That's a really important practical question. The paper focuses on killing the plants, but the implied advantage is the speed. Because the exposure is so short, potentially just 10 seconds, the idea is that the intense heat doesn't have enough time to transfer deep into the boat material itself and cause damage.
Ah, okay. It's like quickly passing your hand over a flame versus holding it there. The duration is key.
Exactly. It's a quick, intense surface treatment. Enough to cook the plant fragment instantly, but not long enough to warp fiberglass or blister paint, theoretically. That needs testing, of course, but the short duration is the protective factor.
So that localized rapid heat gets around the damage issue you'd have with prolonged soaking while still being way more effective. It solves the practicality problem.
That's the hope. It makes effective decontamination feasible for large, complex items.
Okay, but like any study, it can't be perfect. Let's talk limitations. What caveats did the authors mention? Where do we need more research?
Good point. The main thing they acknowledge is that their tests used fairly standard-sized apical fragments, tested individually or in small clumps.
Meaning,
Meaning, if you have a really large, dense mat of weed tangled around your propeller, or maybe species with much thicker stems, or plants that have parts growing above water, which might be tougher.
right, those might need a bit longer than 10 seconds.
Possibly. The heat needs to penetrate. So maybe for those really big clumps or tougher plant types, you'd need 20 or 30 seconds. Still incredibly fast, but it might need adjustment based on the target. The principle is sound, but the exact timing might vary.
Makes sense. What else needs checking? It's not just about visible fragments, is it?
No, and that's critical. The next big step is testing steam against all the life stages, especially the microscopic ones, seeds, spores, eggs, tiny larvae like zebra mussel veligers. These are often even harder to spot than fragments and can be really tough, resistant to drying out.
And invasive species aren't just plants.
Absolutely not. We need to know if steam works on problematic hitchhikers, like parasites or pathogens. Think about things like the salmon fluke, Pterodactylus salaris, or viruses like rhinovirus that affect amphibians. Can steam kill those too, preventing their spread on contaminated gear?
That would be huge. And finally, proving it works out there, not just in the lab.
Yes. In situ trials are essential. Setting up these steam stations at actual boat ramps, testing them on real fishing nets, kayaks, boats, including dealing with marine biofouling on yachts. We need to see it work effectively and efficiently in the messy, real world.
Okay, so let's bring it all together. The big takeaway from this deep dive seems clear. A super short blast of steam, like 10 seconds, looks like a powerful, simple, chemical-free way to kill invasive plant fragments.
Fragments that cause literally billions in ecological and economic damage every year.
It really could change the game for biosecurity just by using basic physics, rapid, intense heat.
It's an approach that really deserves serious attention. Biosecurity groups, policymakers, managers of waterways, they should be looking hard at promoting and adopting this. It offers a practical solution to a really stubborn problem.
Which leaves us and you with a final thought to chew on. We know that compliance with the current check, clean, dry methods is, well, let's be honest, it's often pretty low. People are in a hurry. 15 minutes of cleaning feels like a chore.
Yeah, it's a barrier.
So how might the sheer speed and simplicity of a quick steam wash, maybe taking less time than tying down your boat, actually change people's behavior? Could that convenience finally lead to widespread adoption and effective enforcement of rules designed to protect our waters? That behavioral shift might be the biggest impact of all.